In this video, we're going to look at possible sources for differential equations. Where do they come from? In the sciences, they come because natural laws and theories are best expressed with differential equations. We're going to explore this by looking at a few scenarios and sentences that come up in the natural sciences and seeing how they turn into mathematics. Here's an example about heating and cooling. The rate at which a potato cools off is proportional to the difference between the temperature of the potato and the air around the potato. This is a standard equation that's used in heating and cooling scenarios. And if we give these terms some variable names, let's call the temperature of the potato H, just because T is a bit confusing with time. Temperature of the air, that we can give it maybe a capital T for T air. We can read this off and identify the rate at which the potato cools off. That is exactly what a derivative means. So dH dt is proportional to equals a constant times, and literally here the difference between is a subtraction or a minus. The temperature of the potato, H, minus the temperature of the air. That's the difference between them mathematically. And notice this is a first order differential equation. Simply by expressing what we think drives temperature change, the fact that a potato is hotter than the air around it, and that difference has something to do with how quickly it's going to cool down, we end up with an equation that has a derivative in it, and our goal would be to predict the function h of t, which is the temperature of the potato over time. So we have an equation, and that would be our solution, h of t. Here's one more from the social sciences, though it has analogs in biology as well. The rate at which a rumor spreads is proportional to the product of the people who have heard it, that's 1 unit, and those who have not. And the idea here is that the more people who have heard a rumor, the faster it spreads, but they have to be able to tell it to someone who hasn't heard it before, and so we include the number of people who have not heard the rumor yet as well. This product is a typical way to map the interaction between two populations, people who have heard it and people who have not. So let's define some variables. Let P be the number of people who have heard the rumor. And if we're talking about the rate at which a rumor spreads, well, that is the rate of change of P. As more people hear the rumor, the number of people per unit time changes, that's dP dt. Let's also let a new variable, call it n, be the number of people who, as you might expect here, have not heard the rumor. If we write this out, the rate at which the number who have heard it changes is proportional to, is equal to a constant times the product of, that just means multiplication, the multiplication or the product of two terms, P and N. And that's it. This expression with some statement about how things are changing over time and why they are changing, modeling an interaction between the people who have heard the rumor and the people who have not, ends up in this kind of formulation. What's a little uncomfortable, of course, is that it's not all in terms of the same variable or constants. This n would be kind of a problem going forward. One of the things that biologists, sociologists would do here is define the total population, which is a constant. And if we imagine people have either heard the rumor or not heard it at all, the people who have not heard it is the total population minus the ones who have. And that lets us turn our differential equation, in particular the n term, into something that only involves constants and P itself. We're going to return to this differential equation several times in the course. So we want to spend some time explaining the rationale behind it for this particular scenario. Let's consider a third example. The rate at which water is leaking from the tank is proportional to the square root of the volume in the tank. So there's a driving force of gravity that pushes water in a tank out, and we're told some information about the rate at which that is occurring. Take a moment to consider the options here. Which do you think captures this statement most closely? And pause your video, take a moment to answer it, and then we'll check in. The rate at which the water is leaking from the tank, the rate at which something would be leaking would be in something like liters per second or meters cubed per minute. Both of these point to natural units of a derivative of volume with respect to time. So definitely dV dt, and is proportional to equals a constant time. So already we would rule out A and C, the square root of the volume. So the key thing here is not to overthink these statements. You're literally translating the words into mathematical formulations. Let's consider another example. As a meteorite plummets towards the Earth, its acceleration is inversely proportional to the square of its distance from the center of the Earth. So let's imagine a meteorite out here at distance r from the center. Which of these equations is best describing the word version of the problem here? Take a moment to answer, and then we'll check in. All right, let's focus on the second half first, just because that's more like what we've seen already. Inversely proportional to the square of its distance, that is equal to a constant times, inverse means 1 over the square of the distance. So we're looking for this kind of formulation, k over r squared, not k times r squared because of the inverse. The next step is it a first derivative or second derivative? Well, acceleration is equal to the second derivative of position, or in this case here, of height, or of distance. And so this would be the second derivative of r with respect to t, and that puts us into answer D over here. Through all of these examples, we're expressing how easily differential equations can be constructed from relatively simple intuitions about how a system works. This is capturing Newton's universal law of gravitation, and it leads directly to a statement about the position over time or the height over time of an object as it's falling. The other scenarios covered biology, they covered physics, they covered sociology, and they were fairly natural ideas for how things work. When we translate them into mathematics to figure out what they would predict, we end up with a differential equation. Thus the importance of this unit in the course and also in future courses. We have several courses at Queen's specifically on differential equations in second year.